So chapter 7 here, we're going to concern ourselves primarily with something called the normal probability distribution. So we'll make some very brief definitions. We've already talked about probability quite a bit previously. We also talked about how can we calculate and compute probability. Is it easy? Is it hard? Well, what we can then do is we can define something called a probability density function. And it's an equation that is kind of used to compute probabilities for certain random variables. It has to satisfy two properties. So what we're going to be doing is we're going to be looking at the graph of the normal distribution called the bell curve. The bell curve is something that's going to pop up quite a bit. The total area of the graph under the equation has to equal 1, because what we're going to find is that the area under the graph is actually going to represent certain probabilities. It's going to represent certain probabilities. And we'll build up and talk about the normal distribution later in this very section. Also, the graph must stay strictly above the horizontal axis, the x-axis. It can never go negative. So again, we're not going to talk about the normal just yet. We're going to actually talk about a slightly different one. Suppose that the United Parcel Service is supposed to deliver a package to your front door, and the arrival time is anywhere between 10 a.m. and 11 a.m. Let this random variable x represent the time from 10 a.m. when the delivery is supposed to take place. The delivery could happen at exactly 10 a.m. or it could happen all the way as late as 11 a.m. So that can happen at time 0 minutes or time 60 minutes from the start. And so if we break that up into 60-minute intervals between 10 a.m. and 10:01 a.m., between 10:01 a.m. and 10:02 a.m., etc., and go down the line, we'd see that there's 60 different possible times, if you go out to the nearest minute, where the package could arrive. Thus, each of those times has a 1 in 60 chance of being it, assuming that they're all equally likely. So your package is just as likely to arrive between 10:15 and 10:16 as it is between 10:40 and 10:41. So what we can say is that, we're going to draw a picture of this situation. What we can say is that we can put a 0 here, and it goes all the way to 60 over here. And now let's look at, in theory, between 0 and 1, there should be a 1 over 60 chance. So what we're going to do is we're going to draw something called the probability function for this, the probability curve. And what we're going to see is that the height of the curve tells you the probability that the package will arrive in that interval. Between 0 and 1 minute, there's a 1 out of 60 chance. So thus, the height of this line here is going to be 1 out of 60. Then if you were to go out to 2 minutes, well, the probability that it would arrive between 1 and 2 minutes after 10 a.m. is also 1 over 60. So the height of the curve stays the same, because you take whatever time interval you want, you go up and you read the height of it on the curve. That's going to tell you the probability. In fact, for any 1 minute interval, the height of the curve stays exactly the same, 1 over 60. So it just creates a flat line here. It creates a flat line with a height of 1 over 60. You can count up all the time up to 60. And so what we're going to see is that if you were to take this basically kind of almost in a way forms a rectangle. If you wanted to calculate the area under the curve, it would be 60, the length of the rectangle, times 1 over 60, this width of the rectangle here, which comes out to exactly 1. So the area under the curve, if we were to try and draw it, if you were to draw this area, the area under that curve sums up to a total of 1, or 100%. Because in this case, it just forms a simple rectangle, because the probability should stay the same for any time interval. That means it's a horizontal line. Moving right along, I'll move this back up. There we go. So for instance, if you wanted to know the probability of choosing a time that is between 15 and 30 minutes after the hour, in other words, if you wanted to know the probability that the package will arrive between 10:15 a.m. and 10:30 a.m., what you would do, you would look for your specific times. So here's 15 minutes. Here's maybe 30 minutes. You would want to find the area of this little piece right here. You find the area of this piece. That's going to tell you what you need. Well, we can see that it's a 15-minute time interval here. It's a 15-minute time interval. Times, well, the rectangle here has a height of 1 over 60 again. So using simple fractions, that just becomes 15 over 60, which you might recognize reduces to 1 over 4. Or 0.25. So the probability, the package will arrive between 10:15 and 10:30 is 0.25 or 25%, which makes perfect sense because you're talking about a 15-minute time period within an hour, which is exactly 1/4 of an hour. It's a quarter of an hour. Since any time has an equally likely chance of being when the package arrives, then you could argue that there should be a 25% chance that the package will arrive in that specific quarter of an hour. So it's quite useful then to think of the area under the graph of your density function, of your probability function, over a given area interval represents the probability of observing a value in that interval. So area under the curve, that's what we're thinking here, area under the curve. So there's all kinds of different probability curves that exist out there in nature. all kinds of different curves that we could appeal to, that we could use. There's the uniform that we just looked at, which just forms a straight line, a straight horizontal line, no drama about it. But there's also a normal distribution curve that creates this bell shape here, the bell-shaped curve. That's one that we can say is also a probability distribution unto itself. It tells us the probability of observing certain values. Now, we overlaid this on this histogram here, but even that histogram is not a perfect bell-shaped curve. We want to look at the kind of maroon line underneath it. So a relative frequency histogram that's symmetric and bell-shaped is said to have the shape of a normal curve. So the normal distribution is what we're going to be talking about. And this is a better picture of it. If a continuous random variable is normally distributed, so if you can think of something that you can say, oh, well, it behaves according to a normal distribution. What that does is that tells you kind of what the boundaries are for how the probabilities can go. It says, oh, okay, well, there's a 50% chance that a value will fall below the mean, and there's a 50% chance a specific value will fall above the mean. There's all kinds of things. We're going to be putting values here along this x-axis here that are going to be based on the mean and the standard deviation of the curve. So we can say that something is normally distributed or has a normal probability distribution if we can model it with this curve. This curve's bell-shaped, symmetric. Don't worry about the term inflection point. It may be one easy multiple choice problem on a homework, but it's not something that we uber focus on or anything like that. But if you're curious, the inflection points occur at one standard deviation below the mean and one standard deviation above the mean. So there's all kinds of ways and manners in which this can behave. You can talk about a normal curve that has a mean of 0 and a standard deviation of 1. It looks like this. The mean occurs right here in the middle. It's also the mode. It's also the median for the normal distribution. So for a normal distribution, the mean, median, and mode are all exactly the same. Over here, this blue one is a normal distribution that has a mean of 3 and a standard deviation of 1. So the shape doesn't change, just the position that it lies along the axis. Here, the means were the same. You have a mean of 0 in each case. Mean 0. But here, the blue one has a standard deviation of 2. And so the larger the standard deviation, the more spread out your data is. So it's kind of like someone just smushed it. They took their hand, pushed it down from on top and smushed it. Here's a standard deviation of 1. The graph's a lot taller. It's a lot narrower. It's not as spread out. But imagine someone took their hand and smushed it. They smushed this thing down and made this blue one here. That would be what happens whenever you increase the standard deviation. So there's going to be quite a bit of things we'll talk about here. We're going to do a couple examples today. I won't just, sorry, I hope this isn't giving you dizziness or something like that. What we're going to do is we're going to talk about the properties of the normal curve. We're just kind of dancing around it. But at the end of the day, it's a probability curve, which means we're curious about the area underneath the curve. That's kind of like one of our key things about it. The whole reason we use the normal probability distribution is we want to compute areas. Now, the problem is the area earlier for that uniform, it was just a rectangle. So all we had to do was do width times height of a rectangle, and that's easy. That's how you find the area. For a curve, finding the area under this thing, how in the heck do you do that? It's curved. It's not straight lines. It doesn't follow a simple circle or a triangle or other shapes that we know how to calculate the area of. Oh, well, that's a great question. That's a wonderful question. That's something that statisticians have to answer. You actually have to use some calculus, and then you actually even have to go beyond calculus because it's said to be intractable, you have to use certain numerical mathematic techniques in order to find the area under this normal curve. Uh-oh, is this about to get incredibly complicated? No, because we're not at that level where we're able to do that. That would take a couple years of being like a math major in college and have studied calculus and then studied some computer programming so you know how to program the numerical technique in order to do that. Obviously, that's not something we're going to do. What we're going to be doing is we're going to be using something called a Z chart or a Z table. So a Z chart or Z table. We're going to use this to find areas underneath the normal distribution curve. Or if you have a sufficiently powerful calculator, if you have a calculator, generally speaking, a graphing calculator of some kind, our calculators can find these areas for us. If it is sufficiently powerful. If your calculator is a sufficiently powerful calculator, we can actually find those areas ourselves. So if you have just the standard scientific calculator, that's a-okay. What you're going to be doing, what you're going to have is you're going to be supplied with a Z chart on any exam, whether you have the scientific calculator or not. And you can do all of these problems using just a Z chart, which means you're going to have to look up probabilities from the table, but it's not so bad. It's not as bad as you'd think. The calculator is nice because you just punch your numbers in and it'll kind of tell you your area, but it's a little less hands-on as a result. So let's talk about a few qualities about this wonderful curve here, and then we'll look at an example. Properties of the normal density curve. It is symmetric about its mean, mu. Check it out. Here's the mean, mu. Over here is mu plus sigma. Down here is mu minus sigma. We'll talk about that in more detail in a moment. But if you take the mean is the value in the very center of it. And as you can see, it's nice and symmetric about that. It looks like someone just put a mirror down and just it's a reflection about its own middle, which is exactly right. That's what it means to be symmetric in this case. So it is symmetric. We also have that the mean, median, and mode are all equal. The mean, median, and mode are all equal, which is kind of interesting. Remember, the median is the point for which 50% of the values fall below it and 50% of the values fall above it. Well, now that we're talking about probability and we're talking about area under the curve, we can graduate that idea and say the median is that value for which there's a 50% chance that a certain value will fall below it, that a randomly selected value will fall below it, and there's a 50% chance that a randomly selected value will fall above it. And since the mean and median and mode are all the same, that's also true of the mean. There's a 50% chance a value will fall above the mean, and there's a 50% chance a randomly selected value will fall below it. So it kind of works out that way. It's pretty interesting. Again, it has inflection points at mu minus sigma and mu plus sigma. What does that mean? We'll look at that in a moment. The total area under the curve. So if you were able to somehow calculate the area underneath this curve, it would come out to exactly 1 or 100%. Also, this graph is a tad bit misleading because it looks like the graph touches the x-axis. In fact, it never does. But when you draw a picture, it's hard to show what's really going on here. In fact, the x-axis is a horizontal asymptote, meaning that the curve will attempt to get closer and closer to the x-axis without ever actually touching it. It'll get closer and closer, but if you were to zoom way the heck in, you would see that it would not touch it. me see if I can perhaps demonstrate that. Give me one moment to whip something up. I can demonstrate that with a graph. Give me just a hot minute. And I'll whip up something that was really cool for you using my magic. Let's see. Okay. And then maybe something a little more milder than that. Okay, so allow me to share my magic with you. So what we can see here, and yes, I play Minecraft. My secret is out. Oh, you can't see it if you're in class, but you can see it on Zoom. I have a little link to my Minecraft. Not anymore. What we can see is this is actually a graph of the normal distribution curve. It's kind of interesting. Now, whoa, look at this. This was the function for it. Oh, get out of here, right? We're not ever going to actually deal with that function, so you don't have to worry about it. But what you can see is that if you go to the right, it looks like, oh man, this thing like touches the x-axis. Oh, actually, it doesn't. If you zoom way the heck in, you'll notice that it's going to get closer and closer to the x-axis. It's trying to approach it. It can get really close, but it'll never quite touch it. Now, the problem is technology is only so good. The technology eventually, there's only so many pixels on a computer screen. So it's going to look like it's touching it. But if you keep zooming in, no, it never actually quite does that. It keeps getting lower and lower and lower. But eventually, it's never going to touch that x-axis. So what we can say is then that the x-axis is said to be a horizontal asymptote for it, which is pretty interesting. Which is pretty interesting if you ask me. So anywho, now you know that. What that means then is actually a random variable, a random value can go off to infinity or negative infinity and still have and it's still possible. But so the total area under the curve is 1. The area under the curve to the right of mu equals the area under the curve to the left of mu, which is 1/2, which makes perfect sense. Here's mu in the middle, which is the mean. Remember, the mean and median are the same here. So there's a 50% chance you're below the mean and a 50% chance you're above the mean. So all that's saying, that's just a re-expression of the idea that we have symmetry here, because the mean is that middle value there. The graph approaches but never reaches the horizontal axis on either end, whether you go to the left or to the right. Now, finally, the empirical rule, which is something we've already discussed before in the class, but now we're going to kind of bring it full circle here. The empirical rule tells us that approximately 68% of the area under the normal curve falls within one standard deviation of the mean, falls between mu minus sigma and mu plus sigma. Approximately 95% falls between mu minus 2 sigma to mu plus 2 sigma. In other words, 95% of the probability falls within 2 standard deviations of the mean. And finally, almost 100%, but not quite, 99.7% of the area falls within 3 standard deviations of the mean. Here's a nice visualization of that idea. Within 1 standard deviation of the mean, 68% of the data falls within there. Within 2 standard deviations of the mean, a total of 95% falls in that range. Finally, within 3 standard deviations of the mean, a total of 99.7% falls in that range. We're going to make use of that quite a bit. We're going to use that empirical rule a lot. So now let's try ourselves an example problem. Let's say scores on a certain test are normally distributed, meaning we can use this curve here. We can use this normal probability curve in order to model the scores. So let's say scores on the test are normally distributed with a mean of, how about we'll make it fun. How about 1200 and a standard deviation of 150. So mu equals 1200. Standard deviation sigma is 150. What we can do is we can actually chart this situation on this graph here. We can chart it. So in the very middle here, in the very middle would be the 1200. So actually, yeah, maybe we need to zoom in instead. So in the very middle would be the 1200, because that's what mu is. And so this means that scores on the test, because that's 1200 is in the middle, that means about half the people who take the test, 50%, fall below the mean. And 50% fall above the mean total. Now, next up, mu plus sigma, this would be, well, 1200 plus 150. That's 1 standard deviation above the mean, which if you do that math comes out to 1350. So here, this value, 1350, is 1 standard deviation above the mean. This value would be, well, 1200 minus 150, which is 1050. So now let's take the entire thing into account. The score of 1050 is 1 standard deviation below the mean. The score of 1350 is 1 standard deviation above the mean, as we can see. So the conclusion we'll draw, 68% of test takers will score between 1050 and 1350. Let me write that out. According to the empirical rule, 68% of test takers will score between 1050 and 1350. That's exactly what that means. So finally, we're putting some actual numbers to this thing. This test, for some reason, you can have a score of 1200. So that kind of makes you think of maybe the SAT or I don't know, something like that, which has, you know, 2 sections or I guess 3 sections now, something like that. So just whatever this test is, it's a weird test that has a weird scale. We can keep going with that idea. We can keep going with that. And let's make that red. No, purple. So 68% of test takers will score there. Next up, we can go 2 standard deviations above the mean. So we can do 1200 plus twice the standard deviation. That's going to be the calculation there. So you can do that. 2 times 150, according to order of operations, you got to do that first. That's going to end up with a 1500 score. And then there's not enough space on this, so I'm going to have to delete that. But basically, a 1500 score is 2 standard deviations above the mean. Down here, 2 standard deviations below the mean, you got to do 1200 minus twice the standard deviation. That's 1200 minus 2 times 150. That's actually going to give you exactly 900. So now, if you score a 900, you scored 2 standard deviations below the mean. And so now what we can see is, well, according to the empirical rule, 95% of the data falls within 2 standard deviations of the mean. So in turn, what we can say is this. 95% of test takers, let's do it in purple again. 95% of test takers will score between 900 and 1500. Just according to the empirical rule. We know what the mean is, it's 1200. We know what the standard deviation is. So I can tell you that 900 is 2 standard deviations below the mean. 1500 is 2 standard deviations above. So a full 95% of the data is under this curve. If I did 13.5 plus 34 plus 34 plus another 13.5, that would add up to 95%. And so finally, if we go 3 standard deviations above or below the mean, you can just add an additional 150 on to what you had before and subtract 150. So 1650 and 750 will be down here. So finally, what we can say is that 99.7% or virtually all test takers will score between 750 and 1650. And that one's fallen off the page. So we'll put these all up here. That's what's going on here. So from as low as 750 to as high as 1650, 99.7% of test takers fall in there. So that's one interpretation that you can take. The other interpretation is you can make a probability interpretation. Let's say I have this test. It has an average score of 1200, a standard deviation score of 150. And let's say I go out and I randomly select someone who just took the test. I say, you come here. I randomly select someone who just took the test. I go get their score. I pull it up and I wait to look at it. I can do some probability calculations. I can say, there's a 68% chance that this single person's exam score will be between 1050 and 1350. There's a 95% chance that they will score between a 900 and a 1500. And finally, there's a 99.7% chance or an almost guarantee that they will score between 750 and 1650. That's what I can do. That's the probability interpretation of this because of how it lays down. Well, this creates some interesting things here. Looking at this chart, we can also say, oh, well, wait a minute. What if I wanted to know the probability that they score within 2 and 3 standard deviations above the mean? In other words, what if I wanted to know the probability? I'm going to erase this. So we got a lot going on this screen. What if I wanted to know the probability they would score between 1500 and 1650? In other words, what is the probability a single test taker will score between 1500 and 1650? Well, we can see that the area under the curve between 1500 and 1650 is 0.0235 or 2.35%. So the answer is 2.35%. Now here's the rub. If you memorize the empirical rule, if you just go up here and memorize this rule here, the 68% within one standard deviation, 95% within two standard deviations, 99.7% within three standard deviations. If you memorize the empirical rule, then technically, theoretically, let me get the numbers back up. Then theoretically, you could reconstruct this chart here. Theoretically, you could do that. You could figure out all these segments because you know within one standard deviation of the mean, 68% of the data has to lie there. And thanks to symmetry, that means that you could divide that into two pieces, 34% and 34%, and say that between one standard deviation below the mean and the mean itself, that's half of the 68%, so 34% falls in that range. Technically, you could reconstruct it knowing that, just from the empirical rule. If you can't, it doesn't necessarily hurt to kind of memorize this chart, to memorize this, but it's better to just remember the empirical rule and you can reconstruct this. Because you could ask all sorts of questions and answer them fairly quickly. What else could you ask? Well, what is the probability a single test taker will score, how about between 900 and 1350? All right, well, looking at it, let's think. Here's the 900, so we'd have to add the 13.5% plus this 34% here plus this 34% here. Because 900 to 1350 has these three segments under the curve. And so that'll be what, 81.5%, something like that. So there's an 81.5% a test taker will score between 900 and 1350. So now just looking at this, do you think it's likely that someone scores an 1800 on this test? No, it's not likely. I mean, 1650 is already pushing it. If you score 1650, you're already 3 standard deviations above the mean. And most of the data is going to fall. 95% of the data is supposed to fall between 2 standard deviations of the mean. So the further up you go, the less and less likely it becomes that you're going to score that. And you can tell because the height of the graph becomes lower and lower and lower. And the height of the graph kind of gives you an idea of how likely it is. The higher a score is on the graph, the more likely that that score is, or in a certain range of values. And so you could keep going. You could say, well, 1800 is not very likely, but neither is 600 way down here, because that's very unlikely on the other end. There's even a couple other questions you could ask. What is the probability a person will score more than a 1650? Well, here you got to look at this. You have to remember that the entire area under the curve adds up to 100% or 1. So let's see, 2.35% plus 13.5% plus 34% plus 34% plus 13.5% plus 2.35%. All these actually only add up to 99.7%, which makes sense because that's within 3 standard deviations of the mean. But there's still a little sliver under the curve way down here. There's a little sliver down here, and the curve actually keeps going and going. There's this little sliver down here as well. And these little slivers come out to a very tiny amount, 0.15% down there, and 0.15% down there. That's what they come out to. So the probability a person will score more than 1650, here's 1650. We need to be above that. So just that tiny sliver alone is 0.15%. And so that's the answer. So it's very, very, very extremely unlikely. 0.15%, that's less than 1%. So that's saying that what, 15 out of 15 out of 10,000 people will score better than a 1650. So it's possible, it's just very unlikely. What is the probability a person will score more than a, well, how about more than a 1350? Well, now we got to add three sections. We got to add, here's 1350. We got to add the 13.5% plus the 2.35%. And that's going to give you something like, that'll give you 2.5% plus 13 is 16%. So 16% of people will score above a 1350 because you can keep going and going and going. So the area under the curve is what we're ultimately looking at, because the area under the curve not only can tell us what percent of people will fall in that range, it also gives us the probability. It also tells us probabilities. In fact, let's talk about that. Suppose that a random variable x is normally distributed with a mean of mu and a standard deviation sigma. The area under the normal curve for any interval of values of the random variable. The area under the curve either represents the proportion of the population that falls in that range of values. So for instance, with scores, hope my chair didn't just break. I guess I'll fall over here in just a moment if it did. Remember we said it could, if we looked at those test scores, we could say, oh, what percent of people fall between, what was it, like 900 and a 1350 or something like that, 900 and a 1650. We could do those kind of calculations, and it can just tell you what proportion of people will fall under that. But the kind of better interpretation, or the more useful one, is the probability interpretation. So you could say the weights of giraffes are normally distributed with mean of 2,200 pounds. So the average giraffe weighs 2,200 pounds. Now I've always asked myself, my girlfriend and I talk about like different celebrities that I could take in a fight. We all, we say, hey, or, could you take this guy in a fight? Nah, could you take, she wants to know if I could take Harry Styles in a fight. I'm like, yeah, I could take Harry Styles in a fight. I have no idea if I actually could, but I'm just going to assume I can because I just have rock star confidence, even if I'm not. Dwayne The Rock Johnson, I will put the people's elbow down on Dwayne The Rock Johnson. I will rock bottom him all the way down to Australia. Yeah, I could take Dwayne The Rock Johnson. Oh, he can bench press me with one arm. Well, I'm more agile. Exactly. They're pretty muscles. They're movie muscles. That doesn't actually make him strong. So we always ask, could you take all these celebrities? I always claim I can take 98% of football players in a fight, and NFL players who are in the best shape in the world, some of the best athletes, some of the strongest people in the world, and I fully believe I could take them in a fight. So finally, the next question is, Josh, could you take a giraffe in a fight? Could I take a giraffe in a fight? A giraffe weighs on average 2,200 pounds. 2,200 pounds. There's a standard deviation of 200 pounds. So could I take a giraffe in a fight? Yes, easily. And why? It's because I'm a human being and I'm smarter than them. So I'll find some way. Just give me like a stick. I'll sharpen it on a rock or something and I'll poke it. So no, I can't take a giraffe in a fight. I'm not crazy. So what we're going to say is that the giraffe weighs 2,200 pounds, standard deviation of 200 pounds. So we can go back up here. We can draw out the normal curve for that situation. Remember, we had a mean of 2,200, standard deviation of 200. So we can label some points on the graph of that. The mean, 2200, would be in the middle here. And then one standard deviation of the mean is 2400. Two standard deviations above the mean would be 2,600-pound giraffe. Three standard deviations above the mean would be a 2,800-pound giraffe. So remember, we kind of talked about there's a 95% chance a randomly selected giraffe will fall within two standard deviations of the mean. So let me complete this chart. There's a 95% chance a giraffe's going to fall between 1,800 and 2,600 pounds. So do you think it's very likely that you could find a giraffe, that you could randomly select a giraffe that's going to weigh 3,500 pounds? No, it's extremely unlikely. Is it theoretically possible? Yeah, it is. Maybe that's a genetically modified giraffe, something made in a test tube and then grown at a zoo. But no, because 95% of all giraffes are going to fall between 1,800 and 2,600 pounds. 99.7% of giraffes are going to fall between 1,600 and 2,800 pounds. It is extremely, hilariously unlikely you're going to find a giraffe that's way above 2,800 pounds like that, but it is theoretically possible. So those are kind of the questions that we can answer about this. We're not getting super detailed about it just yet. But now we'll shade the area under the normal curve. We don't have to worry about that. Suppose the area under the normal curve to the left of 2,100 pounds is 0.3085. That's going to be true, but we can't necessarily see that here because that's actually half a standard deviation. So remember, 2,200 was here, 2,000 was here, and so 2,100 would be half a standard deviation, and we don't have the tools for that yet. But suppose the area under the normal curve to the left of 2,100 pounds is 0.3085. What this means is that if I go out in the wild and I randomly select a giraffe, I don't know how you're going to randomly select one, but you could. If I go out in the wild, I randomly select a giraffe, there's a 0.3085 chance that it will be under 2,100 pounds. So if I randomly select a giraffe in the wild, there is a 0.3085 or about a 30.85% chance that giraffe will weigh under, oh my goodness, 2,100 pounds. Now, for me to have a chance in a fight against a giraffe, it would need to weigh under like 300 pounds. So am I likely to find a giraffe in the wild that I can take? No, I'm just not. I assume though these weights are for fully grown adult giraffes. No, it's not going to happen. I'm not going to find a giraffe that's under 300 pounds. And even that's pushing it. I mean, have you ever seen a giraffe run? They can run at like 45 miles an hour. Now I have a car that can go faster than them, but I'm not giving myself a lot of chances against a giraffe, but I have thought about it. I probably dreamed about it as well many times. Okay, so one homework problem we'll look at. Is going to involve the normal distribution again. Now this is cool. You can zoom way in on this, or you can open up a separate picture of the normal curve for this specific situation. This is number 14 on your 7.1 homework. Now your numbers might be a little different because it randomly generates the numbers, but the process is going to be similar. So the figure to the right represents the normal curve with mu equals 266 and sigma equals 16. Why? Well, suppose the lengths of human pregnancies are normally distributed with a mean of 266 days and a standard deviation of 16 days. So that's kind of interesting. The average pregnancy lasts about 266 days, but not every single pregnancy is going to be exactly 266. But it's also very unlikely you're going to get a pregnancy that's way far away from 266. It's possible, but it's just not likely. So there's a few things we can say. If the standard deviation is 16 days, then there's a 68% chance that a randomly selected pregnancy is going to last between 16. There's a 68% chance that a randomly selected pregnancy is going to last between 250 days and 282 days. So there's a pretty good chance you're going to be in that range of values if you're pregnant. If you go 2 standard deviations below the mean, and I will use my wizard math. There's a 95% chance that a randomly selected pregnancy is going to last between 234 days and 298 days. So you can kind of see the normal distribution, because it says it's normally distributed, applies here. Now they're coming up here and they're talking about a value of 290. Well, 290 is not exactly a given number of standard deviations away. 298 is, and then we said 282 was 1 standard deviation below the mean. So let's see, 1 standard deviation above the mean was 282. 2 standard deviations above the mean was 298. And they're talking about the number 290. Well, that's okay. We don't yet have the tools to calculate a probability that isn't centered around one of those simple standard deviations, because 290 is going to be exactly 1.5 standard deviations above the mean. And we don't have a rule for that yet. The next section, we will talk about the rule for that. Anywho, it's going to have to give you a probability value in this particular case. So provide one interpretation of the area using the following values. The area to the right of 290 is 0.0668. So what we can say, since it's the area to the right, we're talking about 290 here, this area to the right of it is the area above it. And it's 0.668. So the proportion of human pregnancies that will last more than 290 days is 0.668, 0.0668. We can provide a second interpretation to that. The probability that a randomly selected human pregnancy will last more, it's not less than, because we're talking about the area to the right. So the probability it will last more than 290 days is also the 0.0668, or 6.68%. And then I don't care about this last one. Well, maybe we'll do it. So now let's look at this figure. They're highlighting the days of 230 and 245. Here's the area underneath the curve between those days. They're saying that the area between x equals 230 and x equals 245 is 0.0825. Let's pick some interpretations for that. The proportion of human pregnancies that will last between 230 and 245 days is 0.0825. So basically 8.25% of all pregnancies last between 230 and 245 days. If you want the probability interpretation, the probability that a randomly selected human pregnancy will last between 230 and 245 days is again 0.0825, or 8.25%. Let's see if we can find some more interesting ones. So this section is pretty straightforward. Let's look at this problem. Suppose the monthly charges for cell phone plans are normally distributed with a mean of $57 and a standard deviation of $20. So we can draw a normal curve for the parameters labeled. If we want to be within one standard deviation, well, 57 minus 20 is 37. 57 plus 20 is 77. 57's got to be the middle value because it's the mean, so this would be the curve for it. The one with 57 in the middle and one standard deviation below, one above. Shade the region that represents the proportions of plans that charge less than $37. Let me see if I can change this. Come on, you can do it, touchpad. Have ye no faith in me? It just doesn't want to. Okay, so looking at that previous thing, the 57 has to be in the middle, 37 and 77 on either side of it. And so the proportion of plans that charge less than $37, we want to shade the area of the graph under 37 and still has the appropriate values here, which would be, looks like this one. Now, it's going to straight up tell you, suppose the area under the normal curve to the left of x equals $37 is 0.1587. So looking at this graph here, here's 37. Here's the area shaded underneath 37. It's saying that that area amounts to 0.1587. The area of this shaded region is 0.1587. So one of the possible things that we can read about that, we'll have to read it carefully. The probability is 0.1587 that a randomly selected cell phone plan in this population will cost less than $37 per month. And then we use less than because we're shading the area to the left of 37 underneath 37, in other words. Okay. That's it for today. Let me take attendance real quick.